So I'll acknowledge them as we move on to the projects. So before we start, I'll give you a quick overview of the Networks and Systems group at LUMS, which I do. So we worked on 3 broad areas. One is cloud computing and data centers. The other is high-speed wireless networks. And the third area is internet censorship. So within these spaces, for example, in cloud computing and data centers, we work on sort of how do you design low latency data center networks. So this includes protocol design, which is especially geared towards low latency. And then we also look at data center architectures, particularly with respect to sort of efficient and receiving data plane control plane designs. In the space of wireless networks, we focus on new challenges as Wi-Fi speed scale to gigabits per second. So at that high speeds, you have sort of user level throughput, which degrades dramatically because of MAC layer inefficiencies. And so we've looked at those, how do you address MAC layer inefficiencies at gigabits per second Wi-Fi, and how do you deal with quality of service differentiation at that speed. And we've also looked at sort of developing regions research, which is about building low-cost data channels. So we've looked at things like data over SMS or data over missed calls. So such kind of low-cost data channels make sense in developing regions like Pakistan, where cost is a major concern. And we've also worked on long-distance Wi-Fi, so extending the range of Wi-Fi to multiple kilometers. And in the context of internet censorship, we've looked at how do we build incentive-aligned censorship measurement systems, and how do you measure the impact of censorship on various stakeholders like ISPs and users and such like. Okay, so that was a sort of bird's eye view of the kind of research that we've been doing in the recent past.
I like your picture.
Okay, so moving on to low latency data center networks design. So we worked on transport protocol design as well as buffer management schemes. So today I'll be talking about our work on PACE. So this is a joint work with Ali, who was my research assistant, and Ghufran, who was an undergraduate research assistant with me. They both are currently graduate students. So Ghufran is at UT Austin. Ihsan is my PhD student, and my colleagues Alex and Fahad. Okay, so in the last decade, we've seen the emergence of these user-facing online services like web search, social networking, and all these services. If you look at them, one of the key goals is to minimize user response times. And why does user response time matter? Because it translates into operator revenue and user perceived latency. So for example, Amazon conducted a study and they found that every 100 millisecond latency cost them 1% in business revenue. And Google found that traffic reduced by 20% due to 500 millisecond increase in latency. So sub-second latencies matter, and they impact user experience and in turn operator revenue. Now the question that comes to mind is that why is the network important? There are many components to latency. Why does the network matter? So if you look at typical cloud applications, they have many distributed components. It's not uncommon for example, a web search query to touch more than 100 machines. And the network can impact application performance. For example, the study showed that 10% of search responses observed 1 millisecond to 14 milliseconds of network queuing delays. Now, this is orders of magnitude larger than typical round-trip times that you have in data centers, which is in the order of tens of microseconds. And so if you look at sort of the larger picture of resource allocation in networks, then you can broadly categorize them into 2 categories. One is fair sharing, which is that if you have a single link and enough demand flows, then you divide them equally, or some notion of maximum fairness or proportional fairness. It is well known that these lead to suboptimal completion times. Therefore, for many cloud applications, these traditional fairness metrics might not be very relevant. On the other hand, you have priority scheduling, which take into account the quality of service requirements of individual flows, which might be delay sensitive, throughput sensitive, and therefore essentially they're based on prioritizing some flows over other flows. They can minimize flow completion times, and there's a large body of work which tries to aim for that. And there's a body of work which also looks at sort of maximizing the number of flows that meet their deadlines. And the reason why it's challenging in data centers to achieve low latency is for a bunch of factors. So one is that if you look at the structure of how applications are written, they follow this largely sort of partition aggregate structure where user request is divided into multiple subtasks across worker nodes, it oftentimes leads to synchronized responses and the well-known in cascade delay. And then you have heterogeneity in traffic workloads. So you have short flows typically that are delay sensitive and long flows that are throughput sensitive. And traditional TCP, it's well known that does not meet the requirements of applications because it requires large queues to maintain high throughput. So if you look at in the last few years, there's a large body of work that has appeared in SIGCOMM that tries to deal with this issue. So this body of work can be placed into two broad categories. So on one side, you have these transport protocols like pFabric and DQ. They can achieve near optimal performance, but are not deployment friendly in the sense that they require changes in the data plane. And on the other side, you have protocols like data center TCP, L2 TCP that are deployment friendly, but are suboptimal in terms of completion times. So the question that we ask in this work is, let's take a step back. Rather than designing yet another protocol, let's ask, how can you design a deployment-friendly and near-optimal data center transport while leveraging the insights offered by all these transports? Okay. So that led us to the design of PACE, which is a transport framework for achieving low latency. So broadly, in terms of division of responsibility, you can have essentially a centralized design where you have a centralized controller that allocates rates to flows. And you have schemes like FastPass and software-defined transport in this category. The challenge with such designs is that you have latency, you have an additional latency going to the controller, which matters especially for short flows. And these are a substantive fraction of data center traffic for many cloud applications. The second challenge is the processing and network overheads that you potentially might run into. The second approach could be a distributed approach, and in this category, you could have sort of functionality inbuilt inside the switches, like in DQ or PDQ, or you could have implementation or resource allocation decisions purely at the end hosts, like data center TCP and L2 TCP. And here are the challenges of suboptimality. So PACE essentially lies in the distributed category in terms of division of functions. And so it implements a distributed control plane for resource allocation. So it has arbitrators that are at the end hosts and arbitrators that are responsible for links between switches and the end hosts. And this distributed control platform essentially allows you to do resource allocation in a scalable manner. I'll talk about how we achieve scalability. And the result is that it requires no changes in switches, achieves near optimal performance, and you can have multiple applications running with different user objectives. Okay, so here's the outline. I'll talk about data center transport strategies in protocols in the last few years that have been proposed, and then I'll talk about PACE design and finally the evaluation of these. Okay, so we found that there are essentially three transport strategies proposed in prior work. One is the self-adjusting endpoint strategy. So this is followed by TCP, data center TCP, least-squared TCP. So essentially the key idea is senders make independent decisions and adjust rate by themselves based on some coarse-grained signals like packet loss, for instance. The second category, transport strategy, is arbitration. This is followed by PDQ, DQ, and Barat. And here the idea is that there's a common entity, an arbitrator or controller, that allocates rate to each flow, given knowledge of all flows inside the network. And then the third transport strategy is in-network prioritization, which is leveraged by or used by pFabric. And here, switches independently schedule or drop packets based on priorities. So these are the three sort of transport strategies used by prior work. Now, unfortunately, existing transports use only one of these strategies. And we show that you can actually combine these strategies and address the individual limitations of these strategies. So let's see what are the pros and cons of these individual strategies. So if you look at self-adjusting endpoint strategy, it's easy to deploy. But the challenge is it does not support strict priority scheduling, which is needed for minimizing completion times. Arbitration, you can achieve strict priority scheduling, but the challenge is that you have high flow switching overhead. So if a new flow comes up that has higher priority, you need to contact the arbitrator and so that the priorities could be changed. So this introduces high flow switching overhead, which we quantify in our paper. The third is in-network prioritization, with advantages that you have low flow switching overhead because it's on per packet basis and it's work conserving. The disadvantage is that the decisions are switch local. And the second disadvantage is that you typically have limited number of priority queues in existing switches, whereas the number of priorities of flows can be much larger. And so therefore, it leads to suboptimal performance. So here is an example of what happens if you use only in-network prioritization. So suppose you have these two queues. There's a high priority queue, and there's a low priority queue. And you have flows that have these priorities. And so the challenge with in-network prioritization is that one of the challenges that you run into is that you have limited number of priority queues. Now, any static mapping that you come up with flow arrivals and departures, this high priority queue, you can have high flow multiplexing, which means more than one flow getting mapped to the highest priority queue, which leads to suboptimal completion times. So any static mapping essentially degrades performance. Now let's see if we combine in-network prioritization with arbitration, how do we address this issue of limited priority queues? So there's an arbitrator that dynamically maps flows to queues. And so the idea is essentially as the flow's turn comes, you map it to the highest priority queue. So essentially in this particular case, this guy is mapped to the highest priority. All the remaining flows are mapped to the low priority. And as time passes, if this guy leaves the network, then you have flow 2, which gets mapped with the highest priority queue. So with in-network prioritization and arbitration, you can address the limitation of having to deal with limited number of priority queues. Similarly, suppose you were to use arbitration only. And here is an example of you have one flow with priority 10 and other flow with priority 20. This is a high priority flow. And suppose the arbitrator allocates this guy 1 gigabits per second, but this flow can only send at 0.8 gigabits per second because of, for example, socket buffer limitations or other end host bottlenecks. Now the challenge is that your network goes underutilized. So it's hard for the arbitrator to figure out non-network bottlenecks. And so that's the limitation, one of the limitations that the arbitration-only approaches run into. Well,
you're saying that the problem is it's not work conserving?
That's true. And if you combine this with self-adjusting endpoint strategy, what you can do is that these self-adjusting endpoint strategy, recall what it does is that senders continue to probe the network beyond the rate that has been allocated to them by the arbitrator. So this guy can actually use the remaining capacity of 0.2 gigabits per second. So self-adjustment keeps link utilization high, even if the arbitration decisions are imperfect. And so in our paper, we show how combining different strategies actually help meet the challenges faced by individual transport strategies. So PACE essentially leverages these insights in its design and combines these 3 transport strategies in a single framework. So the key design principle that PACE follows is that each transport strategy should focus on what it is best at doing. So arbitrators should focus on doing interflow prioritization at coarse timescales. They should not be doing prioritization at fine-grained timescales. Similarly, endpoints, they should probe for any spare link capacity on their own, in case, of course, you have end host bottlenecks. And in network prioritization, they should be focusing on per packet prioritization at sub-RTT timescales. So all of these strategies have different roles, and they should focus on that. So here's the overview of how PACE works. So there's an arbitration control plane, which is completely decoupled from the data plane. And this arbitration control plane assigns a reference rate based on all the flows in the network, or all the flows that are traversing a particular path, and the priority queue to the flows. Okay. And there's a self-adjusting endpoint strategy, which is essentially guided rate control. So the end hosts use the reference rate, plus they probe for any additional capacity that becomes available. And they leverage existing priority queues for sub-second or sub-RTT type prioritization. So these are the 3 key building blocks of PACE. So like I mentioned, the arbitration is distributed. So every link has a corresponding arbitrator, which may be which can be implemented at the end host or on dedicated host inside the data center. And so essentially for each link, there is an arbitration decision, and the sender sends a data with the minimum rate and the priority. Now, the three key challenges, like I mentioned, with arbitration-based approaches. One is the arbitration latency. The other is the processing overhead at the controller. And then the other thing is the network overhead. Now, what PACE does is that it leverages the tree-like structure of typical data center topologies to address these challenges. So let's see how PACE addresses these challenges. So the first thing that PACE does is that it does arbitration in a bottom-up fashion. So the arbitration moves from leads up to the roots. So consider the scenario: there's a sender and there is a receiver, and this is an inter-rack scenario. So you have Tor switches, top of rack switches, aggregation switches, and core switches. The way arbitration proceeds is that the sender does arbitration for the left half of the tree, and the receiver does arbitration for the right subtree. And these red arrows show the how the arbitration messages move up essentially. So, and the receiver sends the decision of the arbitration to the sender. It combines both the views of the left side and the right side and sends at the minimum rate, which is given to the sender.
Is this is this like per flow or per path?
This is per flow.
I see.
Now, the advantage of such bottom-up arbitration approaches is that for intra-rack scenario, you don't need any external arbitrator because the endpoints can do arbitration on their own. Now, this is a major benefit because a sizable proportion of data center traffic is intra-rack. Because of rack locality, you like to keep latency low, and therefore this is a major advantage that PACE introduces. No external arbitration is required for intra-rack scenarios. For inter-rack scenarios, we introduce optimizations that reduce the overhead. And let's talk about these optimizations. So we talk about early pruning and delegation. I'll only talk about delegation in this talk. Okay, so let's see how delegation reduces the arbitration overhead. So the key idea with delegation is that you divide a link into virtual links and delegate the responsibility to child arbitrators. So for instance, suppose you have this topology. For reservations on this particular link, this responsibility is delegated to the child arbitrators. So based on the demand on these links, the portion of capacity that they can allocate is, for example, A1, this guy A2, and this guy AN, and so on and so forth. So the link capacity is split into n virtual links. Parent arbitrator delegates virtual link to child arbitrators, and child arbitrator does arbitration for the virtual link. And this virtual link capacity is periodically updated based on the demands of these particular links. So the key reason why delegation sort of reduces the overhead is because it tries to make the arbitration decision as close to the sources as possible. So it reduces the arbitration latency substantially. So to quantify this in our paper. If you look at the PACE end-host transport, it uses the reference rate as the pivot rate around which it decreases the rate, and follows data center TCP control laws beyond the reference rate. And it needs a new loss recovery mechanism because packets in low priority queues can be delayed for several RTTs. And for this purpose, we experimented with, we evaluated using large RTOs and small perks for reducing spurious timeouts. So putting together, PACE introduces an efficient arbitration control plane, a simple TCP-like transport, and it leverages existing priority queues inside switches. So we implemented PACE in a small-scale testbed and also carried out NS2 simulations. We evaluated PACE over web search and data mining workloads, and did comparison with deployment-friendly transports like data center TCP, vSquare TCP, and with best-performing schemes like TFABIC. So here's a graph of the application throughput, which is the fraction of flows that meet their deadlines on the y-axis. On the x-axis, we have the offered load, and the comparison of here is a comparison of PACE with data center TCP and vSquare TCP. So vSquare TCP has an explicit notion of deadline awareness in it, and data center TCP does not. So the key takeaway from this graph is that PACE is deployment friendly, but it yet it performs much better than existing transports. Here's a graph of the average flow completion time on the y-axis. And this is the offered load on the x-axis. And this is comparison of pace with p-fabric. And here, the key takeaway is that the pace performs comparable and with p-fabric and sometimes better, but does not require changes in the data plane. So in summary, so we identified key strategies that are used by existing data center transports. And we show that these are, in fact, complementary if you combine them, and it can help address the issues that these individual transports face. And PACE combines these strategies and results in essentially an efficient arbitration control plane, a simple TCP-like transport, and leverages priority queues. And its performance is comparable or better than existing transports. So that's for the first project. Perhaps we can take some questions.
Can you go back to the p-fabric slide?
Sure. So these are the percentage improvements.
What's the baseline?
So the baseline is PACE, because PACE outperforms p-fabric in all these, across all these loads.
It outperforms p-fabric.
Yes.
Like this. Are these on the p-fabric evaluation scenarios?
Absolutely. Yes.
Wow, that's great.
But I mean, that's not the sort of the. I think the main key takeaway from here is not necessarily that PACE outperforms p-fabric. It's more of that p-fabric does not require changes in switches. It does require changes in switches, whereas PACE does not. Yeah. Yes.
So I guess I might be wrong, but based on what you said, you need this time that for the arbitration messages to go there and to get the response, right? You also include that in these numbers in terms of the average completion time.
Yes, they're all included.
I have a question. So the delegation splits a link into virtual links, and then essentially what would happen is that each server, when they want to run an application, they go to the closest arbitrator that has the virtual link corresponding to that, and then gets that information, right? What would happen if there's a area of the data center where there's a lot of a lot of traffic coming from that data center, right? They're all going to be using the same virtual link. So what happens to the other ones?
Right. So what happens is that if from one child arbitrator there's more traffic coming, in the next RTT it'll get a larger fraction of the capacity.
I see. Okay. So this periodic updating of the virtual links is happening per RTT.
Exactly.
Okay.
That's right. Yes.
Did you look at the tail flow completion time?
Yes, we did.
How did they compare?
In terms of tail completion times, actually PACE performed even better. So in comparison to p-fabric, as you know that it sends at line rate, and the tail latency gets pretty worse. So at the tail, PACE performs quite well actually.
Did you see any difference by short flows versus long flows?
So we actually showed completion times of both short flows separately as well as overall completion times, and PACE performed comparably with p-fabric in general. But in terms of tail latency, PACE was even better.
Back to the previous question. So for short flows, essentially if you have p-fabric, it would send the shortest flows pretty quickly, right? In your case, you have essentially one extra not round trip time, but close round trip time because of the arbiter message, right?
Right. So that's a great point. So if you include the delegation optimization, that means you only require 2 hops. So if you're going inter-rack, you would require essentially 2 hops only, which is a small fraction of the overall round trip time. If you're going intra-rack, you have no additional sort of overhead. So that we did not find that was substantive.
So the case where it's just a simple request response, you still have this. You sort of doubled your overhead, or doubled your sort of network usage or your latency.
For intra-rack.
For
intra-rack, you don't need any additional sort of because that's just the first exchange that you have, and you have the arbitration decision.
Yeah, but you have to wait for the decision rather than just sending it.
Yeah, but you still need time to set up the connection.
Right. Well, I was just suggesting that in a lot of RPC scenarios, you sort of they're basically everything fits into one packet. You just send one packet and just get the AG,
Right.
or
Right.
not. So that's something that, if you look at a lot of the way a lot of things are, like data center or networking is moving to things like RDMA and even things like, web requests, RPCs in general, a lot of them sort of follow this pattern.
Yes. So if you have long-running persistent connections and you're sort of having more flows on the same connection, then yes, then you would have to have the extra router time. But the optimization that we introduced in that case was you send at the line rate, but you correct your decision very quickly. So that's one thing that we did in PSP also. You send, but you correct that very soon. So yeah. So we had that in mind and we introduced that. Yes.
Are these simulations is this based on like actual endpoints? Like, what's the setup for this experiment?
So these were NS2 simulations, and we also carried out testbed experiments.
Okay.
Yeah, but these were NS2 simulations.
Okay. So you must have seen the difference in the reference rates only in the testbed, right? Like the NS2, did you see any difference between what the endpoints were actually sending and what rates they got from the arbitration?
So we didn't exactly look at that, but as far as simulations were concerned, we did not have any end host sort of bottlenecks. So I think they pretty much followed the rates that were allocated by the arbitrators, and perhaps maybe within a certain fraction of that. But when you have real end host bottlenecks, then you could have rates which would vary more substantively beyond the reference rate.
How important was that end host involvement in the testbed? Like how often did you see that you needed to adjust the arbitrator?
We didn't really quantify how often the set adjusting at endpoint strategy was useful. But we can imagine scenarios where this would be problematic. Certainly, for example, if you have within an RTP a certain burst of flows arriving, then you would like to react much faster, and self-adjusting endpoint strategy provides you that. You can back off much faster, whereas with arbitration-only approaches, you can have a significant degradation in performance.
Yeah, let's move on to the second part. We can take it offline.
Okay. So the second project, this was work done by two brilliant undergraduate students, Ayyub and Ihsan, and my colleague Qazi is sitting here. So in this work, we essentially presented a case for building a system called Seesaw, in which we combine censorship measurements with high-performance circumvention. So if you look at these services like Facebook, Google, Twitter, Wikipedia, here in the US, these are used by essentially, you get uninterrupted access, but beyond, if you look outside US and Europe, if you pick a person randomly, it's quite likely that at least one of these services might not be accessible. And in fact, people have done studies to show that more than 70 countries actually use some kind of censorship. So if you look at the censorship research landscape, one common research challenge is how do you measure censorship? Here the questions are what is blocked, where it is blocked, and how it is blocked. The second research question is with respect to circumventing censorship. How do you bypass blocking? Now the challenge is that with censorship measurements, you need widespread measurement points, and these are particularly hard to get because oftentimes you need these vantage points within censored regions because censorship can vary very widely in terms of how it gets implemented. And secondly, the challenge with existing circumvention approaches is they are not adaptive to the blocking mechanism, so they apply one-size-fits-all approach, and as a result, they can be quite inefficient. So here in this work, we asked the question, what did we combine them? What if you combine censorship measurements with circumvention in a single platform? So consumers or users benefit from the circumvention system, and then you have the measurement data, which benefits political activists, researchers, human rights organizations, free speech NGOs, and so on and so forth. So that led us to the design of Seesaw, which is a platform which does exactly that. And the reason why Seesaw can be effective is because of this feedback cycle. So you get some measurement data about the blocking mechanisms, and it allows you to circumvent the blocking which is being used. And this high-performance circumvention actually incentivizes users to actually opt in and use our platform. And as more users join the platform, they crowdsource information about how things are getting blocked, and this in turn improves the circumvention approach. So here's an example of adaptive circumvention. So suppose there's a user who wants to access a particular URL. So one of the approaches that are typically followed is that you use a software system that makes use of some relays. For example, Tor, a static proxy, Lantern, etc., etc. Or if you knew exactly how your ISP was blocking content, you could use local fix. And what Seesaw does is that it chooses the best approach that is there because it's data-driven and adaptive. And I'll show you our case study where we try to quantify the benefit of a system like Seesaw. So we did a case study related to Pakistan. So Pakistan gets international bandwidth from two ISPs. So we've called this ISP ISP-A and ISP-B. And so as you know, that YouTube is banned in Pakistan. So in ISP-A, the way they do blocking is that HTTP traffic can access YouTube via HTTPS traffic, HTTPS, but you can't access YouTube via HTTP. So that's how ISP-A does blocking. And if you look at ISP-B, it blocks both kinds of traffic, HTTP and HTTPS traffic. But you can use domain fronting here to bypass the censorship. So we did measurements at the university campus in Lahore. So that's this place where our university is. And this is served by both the ISPs, ISP-A and ISP-B. And we also did measurements at a home user in Karachi, which is served by ISP-B only. Okay, so there are three insights that we draw from our case study. One is that the existing circumvention methods we found that imposed very widely different overheads. And so Seesaw, what it does is it chooses the best circumvention method, which is there at that time. Secondly, we found that censorship mechanism varies with content type, even within the same ISP. And here, the strategy that Seesaw follows is to adapt the circumvention based on the kind of blocking for a particular URL. And blocking mechanisms actually differ by ISPs, even for the same site, and for ISPs within the same region. And here we propose to leverage cross ISP links. So I'll talk about these features in detail in the next few slides. So here's the preliminary design of Seesaw. It's essentially a browser extension, and there's a local proxy running. So there's a learning module which measures the blocking, the way the ISP is blocking content. And then there's a distribution module which uses these measurements to figure out what's the best circumvention method that you can use. So the proposed features are as follows. You use history information. So measurements taken at the local user benefits the browsing of the user. And because it maintains local database of previous measurements. And then these measurements could also be shared to the community of other community users that can bypass using those measurements. And we explicitly account for user consent. So there's informed user consent, and only those URLs are tested which the user visits. So we don't test any other URL which the user is not visiting. And for exploiting cross-ISP links, we take explicit user consent. So here are the results from the case study. So here's a comparison of Seesaw with static proxies, which is very widely used in Pakistan for accessing censored content. So what we did was we fetched the YouTube homepage. These were 200 runs. This was over ISP-B, which blocked both kinds of traffic. And Seesaw used HTTPS with domain fronting. and the measurement point was the campus network. So here is a CDF of the page load times. This blue curve is that of HTTPS with domain fronting, which Seesaw used. And these are different static proxies that we experimented with. They were in the US, Germany, Netherlands, Japan, UK, etc., etc. And the key takeaway from this slide is that we found that all static proxies for these experiments exhibited longer page load times compared to Seesaw, which used the knowledge of the blocking mechanism to use HTTPS with domain fronting rather than using any relay. We also performed comparison with Tor. So here is a graph. Here's a CDF of the page load times. And these curves correspond to different Tor exit points, which were in Canada, France, Germany, Netherlands. And we found that the Tor resulted in much longer page load times compared to Seesaw that used HTTPS on ISP. And here is a result for the case where you leverage cross ISP links. So here's the setup is that there is a home user which is directly connected, which is getting internet service from ISP-B, and therefore uses HTTPS with domain fronting. And there's a cross ISP link, which is served by ISP-A that uses HTTPS. So what this home user does is that it uses this cross ISP link to access YouTube via HTTPS. So in this particular set of experiments, what we observed was that cross ISP links can actually reduce page load times, and these are geographically very nearby. And they could actually result in much lower load times compared to, for example, Tor. So in summary, Seesaw addresses this challenge of how do you gather these widespread vantage points from within sensor regions to report back measurements, and by providing users with high performance circumvention. So by the knowledge of the blocking mechanisms, they can adapt the circumvention method according to how it's being censored. And so this high performance, is actually likely to incentivize users to actually opt in. And as this system evolves, more users enter the system. They crowdsource more information, and therefore the circumvention method actually improves. So here are some discussion points. We only dealt with distributed censorship, but there are places like Iran where you have centralized censorship. So what can be done there? So one of the things that you can do there is to leverage cross ISP links that are international. So for example, you could have peers in Pakistan. So Iran and Pakistan are neighboring countries. So you can leverage inter-country and nearby ISP links for circumvention. One way of addressing this is that you can eliminate or mitigate the impact by the multi-work. If many people are reporting measurements from the same region, then they can crowd this bad guy. But of course, the assumption here is that it's the bad majority. And if the Seesaw decides to use a relay, how to select it, how do you balance, load balance across relays? Because one challenge that you can have with cross ISP links is that if everyone starts using a cross ISP link, the ISPs there will be an increase in ISP load, and they might actually start blocking, the traffic. And there are, despite the fact that we incorporate explicit informed user consent, there might be implications for the end users if the governments decide to run after them. We acknowledge that. There could be anonymization that you might want to use. There's a challenge with how do you store measurement data? What exactly must be stored? Why wouldn't an adversary block our ISPs and take measures against Seesaw? One of the things that we think is that as you scale, this might become harder. But yeah, so that's what I had. And quickly, I'll talk a little bit about NSG and my students. A couple of slides. So all this work is by these fantastic folks. These mostly undergraduate students who have done sort of endless hard work, and they have so there's a considerable focus on undergraduate research at LUMS. So all these names in reds are essentially undergraduate students, and I've always been super inspired by how much they could do. And so we have had sort of PhD admissions at leading places, master's admissions, and industry placements directly from undergrad, and awards. So that's all I had. So I'm open to questions.
You sort of asked most of the questions I had to yourself already. So, but I'd be really interested in I don't know, any of your thoughts on any of the things you mentioned, because those are all questions I had as well. Though I know it's ongoing work. And
right. Yeah. So like I mentioned, if you go to the slide, so we are currently actually working on releasing the first prototype of Seesaw. So for centralized censorship, like I mentioned, we're leveraging cross-ISP links that are international. As far as malicious users are concerned, this is a real challenge. We don't have a very good solution. That's one of the solutions that we essentially came up with, but we're not sure how effective it would be as we go on. As far as load balancing is concerned, I think it should be a relatively simpler challenge, because if you have multiple options, then you can decide which relay to pick to load balance stuff. But as far as deployment risks are concerned, yeah, this needs to be particularly taken into account, because in some countries this might be really problematic.
Yeah, I would definitely say that leakage of user data is a huge problem, and that one of the main, Tor is obviously less efficient than a lot of other blocking schemes, but its goal is to provide better privacy and anonymity for people who really will face retaliation if I don't know, maybe not for going to YouTube, but potentially if they I guess watch the wrong videos that are terrorist videos or democracy videos or whatever.
You're absolutely right. I agree with that. That's true. One of the things that we were looking at is how important is anonymization. So what we observed was that for some users, anonymization, they use Tor as a circumvention tool rather than an anonymization tool. But for many, of course, they use it for anonymization as well. So
what about geo-blocking? Like, for example, when it actually might be Yahoo or Google that's censoring the search results that you get in a certain country because because of the laws of that country. They're like, well, we comply with local laws, therefore we've blocked you from this content. Or even things like, well, when I went to the UK, I found I couldn't watch Netflix even though I had a subscription, which I found very irritating. What do you think about geo-blocking? Or censorship that's not necessarily done by the ISP, but sort of done more at the edge or at the server level?
Yeah, I think that's a great question. I don't have a good answer. I think
sometimes DNS is used as well.
Yeah, we dealt with DNS blocking, but as far as blocking at the server is concerned, where you are only showing some part of the search results and not others, that's a harder challenge, I think, because the content provider itself is sort of restricting access to, but perhaps. Via the usage of relays and Seesaw, you can do search results from other countries where all the search results might be accessible. Perhaps that could be done.
So if you are using a Tor or a static proxy which is located in a country outside your own country, then even the source, for example, Google or Facebook, whoever is serving the content would think that the request is coming from this other country, and they will probably not block it. Yeah, but there was a huge debate going on where you should block this, but when ISPs started blocking YouTube and porn websites in Pakistan, there was a big group of people saying that it should be up to the users. They should block it on their own end rather than doing it in the middle. And then the other extreme is to do it at the source where the video is served from.
Yeah. So one of the future works we're looking at is sort of the impact of censorship on advertisement, because you get all these different kinds of ads, and there's a loss of revenue to to the advertiser and so on and so forth. So that's one of the interesting things that you're looking at as well. Yes.
Related to that, so it just seems like right now what you talked about is kind of a public service that's at risk of shutdown, depending on like how it impacts people. So all advertisements. What do you think can be research value that can be drawn from this database?
Yeah, so I think one of the research value that you could draw is to carry out a longitudinal study of how censorship evolves, in countries, for example. So this is something that researchers oftentimes would like to use, and for example, the Open Net initiative carries out such studies as well. The other thing is that you can figure out how the blocking mechanism itself evolves over time by ISPs. So there is both overt and covert, blocking, which is used by governments. So you could perhaps figure that out over time.
Okay,
how that
I see.
evolves.
So it's not that the mechanism for having Seesaw there is difficult, but it's that by having Seesaw there, you can get data which otherwise is unavailable.
Yes, and the other thing is one interesting thing that we have sort of brainstormed within ourselves, but is that how do you come up with circumvention methods by using machine learning techniques that might, as new blocking mechanisms evolve, can you come up with dynamically with new circumvention methods? Not sure. Perhaps there is a case for doing that.
Okay.
Do you have numbers on the potential size of your audience that would use such a program or software, for example, for Pakistan? And another question would be, this is something like an arms race. So the better you get and the higher the percentage of the population is that uses those services, the more will the centralized or the censorship agency try to take measures to block that again.
So you made a perverse effect of making censorship much better if you're successful in some sense, right?
Yeah, I think that's a very valid point. That might actually happen. So we tried to figure out why ISPs use differential blocking mechanisms in the first place, which is a fundamental question that But I think the reason we found out was that one is cost considerations and human resource considerations. So, for example, in Pakistan, through conversations, we figured out that people did not upgrade their censorship technology that they used because of cost, because human resource wasn't trained in such like. So that's also one of the things. But with respect to your first question, I don't have the numbers. Pakistan has a decent sized population of about 200 million. But what we want to do as of now is that we want to unroll and see how deployment takes up. So that's one of the things that we are also trying to see how much of an incentive is it for the users to actually use Seesaw.
But do you have an idea of how large the percentage of the internet users is that are using existing solutions? Is it in the range of 5-10%, or is essentially everybody using these?
So I'm not sure. Maybe Satash knows because he carried out a measurement study, 1 year earlier at AMC.
So so there was another work in which we measured the impact of censorship, not in terms of number of users, but one of the things that we looked at was how did the traffic on secure channels increased or decreased. So prior to YouTube block, about 7% of the traffic coming out of one particular large ISP that we did the measurement study on, about 7% of the traffic was secure traffic. And after the YouTube block, it rose up to 30%. So this 30% number is exactly 1 year after the YouTube blocking happened in Pakistan. So we were lucky that we had data from before the YouTube was blocked and after it was blocked, so we could make a comparison. This percentage is available, and there is a bunch of how it impacted the ISPs because ISPs were using caches and their networks provided by YouTube, and when YouTube was blocked, obviously the desire for getting the video content did not. People went to other websites for Dailymotion and Vimeo. So the traffic to those websites increased, but now the ISPs had to go and get the content from outside Pakistan. So the cost, it costed a lot of money to them. Yeah.
Mm-hmm. So I had a question on the measurement side. I know it's sort of the beginning of the project, but do you see any sort of global or local trends in censorship based on the measurement or data that you have so far?
Yeah,
or any just sort of interesting things you've noticed?
Yeah, so there was a study conducted by some researchers at Stony Brook University and I think at Princeton, and they found that, for example, distributed censorship in Thailand, in Kyrgyzstan, in UAE, and how it evolved over time. And so there was both, so some of the censorship that they were doing was announced to the public, and others, like political discussions and forums, it was not explicitly announced, but they were doing it. So yeah, I mean, there has been some studies looking at how things have evolved over time with respect to censorship. Some have moved from sort of distributed censorship to more centralized infrastructure. So South Korea has been known to exercise centralized censorship, as well as Iran. So these are two countries that we know of that exercise this kind of censorship. And for those folks, you need sort of peers outside.
And another very interesting thing that we noticed is that in Pakistan, YouTube was being blocked initially by blocking the set of ISPs that belong to YouTube. But then the infrastructure at Google changed.
Now any Google server is YouTube, basically.
Yeah, it's
so
YouTube.
if it's HTTPS and you don't do whatever the URL hits,
yeah.
I don't know how you can block YouTube without blocking all of Google.
Exactly.
That's right.
That's
so and they did not want to block entire Google, because a lot of universities and organizations, they're using email services and all the other services from Google. So they only wanted to block YouTube. So now they are not doing IP blocking. So that's why they switched to doing URL keyword blocking, so they can block HTTPS and HTTP and HTTPS blocking. For HTTPS blocking, they have to do deep packet inspection. That's why one of the service provider was doing it, the other one was not doing it. They did not have the equipment for DPI. And
I'm not sure how you do DPI and HTTPS without the URL hints, without unless you're the NSP and have factored some really large prompts.
Yeah. So what they were doing is that they were by using DPI, they were looking at the fields which were not encrypted. So for example, SNI field is not encrypted. Yeah.
What I'm saying is, if you don't use SNI, it's optional.
Yeah. Well, now with Quick, there's no SNI.
Yeah.
Yeah, and the newer version of TLS. Yeah.
Katrina Leclerc has shown that with
Oh,
very simple classifiers.
Yeah. I call it shallow packet inspection, but yeah, I think that's the only thing that will work is looking at traffic patterns where you can't actually look inside. Yeah.
That's correct. Yeah.
Deep learning, Bob, can do anything. You put what you know into the neural network and.
Oh, okay. I guess that's learning. I don't consider usually deep. Okay, I consider that traffic statistics, not traffic inspection, because you're not actually looking at the content. But I guess one's sort of more measurement, and the other is actually looking at the bits. But yeah.
And the
inputs are deep learning.
You think?
And the funny thing with the Google infrastructure is that if you change the SNI value to anything that belongs to Google, they don't care, because they look at the host field, which is encrypted. They look at the host field to make the backend decision, where this request should go to.
Yeah.
So yeah, I mean, we did some experimentation with that. We could prove that. That's exactly how domain fronting works.
Yeah.
So Ihsan, in your first part of your talk, you showed very effectively that your endpoint-based solution beats even the very best switch-based congestion control, this P-Fabric. There's a lot of people here who work on switches. What can they make?
Get another job.
So actually,
You're like the leading SDN guy in this room. I mean, is there any point to work on switches? If you were working on switches, what would you do?
absolutely, I think there's certainly a lot of value in working in switches.
I mean, Muhammad, we all like Muhammad. He worked very hard, and you blew him out of the letter without touching the switch at all.
No, so I think let me place this in context. I mean, so our solution is not only the end host solution. What we're doing is the functionality which was in the switches, we say move that functionality out to these arbitrators who are now not co-located in the switches, but in standard servers, and use their decisions to build a distributed control platform. But if you get like with works with works on programmable data planes, I think you can have higher speeds, much better performance.
Well, yeah, that's sort of my question, I guess, SDN perspectives is, well, suppose you have a more programmable both control and data plane. Could it, and switches that could maybe give you more information, could that help you out? Hopefully the answer is yes, otherwise I guess we can't get other jobs. But
I think that's a great question to ask.
I mean, like last week, Nandita talked about, using RTT and Google's RDMA network. You probably saw it at SIGCOMM, which maybe is a good idea, if you have switches that can do it, which Google certainly does.
Yeah. So I think, the way I think is that, I think besides sort of resource allocation, there could be other things that the switch also performs. So I think there could certainly be a value in having a more richer, intelligent data plane in terms of performance as well. I think one of the things that you buy with rich data planes is getting rid of these control loops, especially that are needed for arbitration. I think that's one of the things that you can buy. It's unclear in terms of quantifiable terms how much performance benefit you will get, but I think there would certainly be value in that.
About the system control has to be in some sense, that maybe things are delayed, but maybe it doesn't really matter too much. For single packets, maybe just send them all through,
yes.
And for longer lived flows, they're longer lived, so the cost of that arbitration is amortized. So maybe, my thought is that in data centers, your round trip time is very low anyway, so it may not be terrible to go to an arbitrator even on a nearby switch, especially, you may not even have networking, and it'll just be the sort of RDMA kind of fabric anyway, and those requests go through the fast path of sort of, the high priority in your network anyway. So yeah, I don't know. I guess my thought is maybe you don't need distributed. It also might be possible that if your switches give you that you might be able to get more fine-grained information to the end host like RTT with every round trip
Yeah, I think the work by Nandita that you mentioned, if you can get very precise sort of information at the end hosts, you can get a better performance. The challenge has to deal with cases where you require coordination. So for example, if you have resource allocation decisions being taken independently by these end hosts, you can have sort of oversubscriptions and these congestion hotspots emerging. So those are the scenarios that I can think of where really this coordination would help, and purely end host solutions might not be ideal, even though they would give you fairly decent performance.
Okay. Yeah. We're running a bit over time, so let's thank the speaker again. Thank you.